If there is one thing that I want you to take away from my P power program is it has to be power factor. A crystal clear understanding of power factor. And let me explain you why I say so. Because when you get to a point where you have a crystal clear understanding of power factor, this is what it is going to do for you. Number one, you will be on top of all the phasor diagrams. Okay, that is a given. When we were dealing with the synchronous machines, with the induction machines, transformer equivalent circuits, with three different types of loads, resistive, capacitive, inductive, the thing that was having the outsized impact on all of those equivalent circuits was basically the nature of load, power factor. You guys agree with me or not? Correct? So if you have a crystal clear understanding of power factor, all the phasor diagrams that we've discussed in this program will be crystal clear to you. Okay? Now that you know all the phasor diagrams, okay, that I have used to explain different scenarios for different types of loads for different machines. And let's keep things simple. We've learned induction motor using phasor diagrams. We've also discussed application and usage or lack thereof of induction generator, right? Using phasor diagrams, we've discussed synchronous motors using phasor diagrams, synchronous generators using phasor diagrams, overexcitation, underexcitation of synchronous machines using phasor diagrams, transformer voltage regulation as to how it can turn negative using phasor diagrams, voltage support, voltage regulation, voltage drop using phasor diagrams. So if you look at all of these broad concepts, okay, they all tie back to power factor. And not to mention a whole bunch of three-phase related problems that can be easily convoluted just by messing around with power factor. Okay, power factor correction, capacitor sizing, and so on. Because this one concept has an outsized impact on a lot of other fundamental concepts. It is almost as important as square root 3 and 30 degrees. Almost. Square root 3, 30 degrees is still more important. Delta Y configuration, obviously, and all of that, because without that, you cannot solve three-phase circuits. If you cannot solve three-phase circuits, I can guarantee you that you're not going to pass the P-power exam. Okay. But power factor assumes that you know that, and it sort of helps you understand that those concepts which are in the upper echelon of understanding. Okay. So I got three variations of same questions, and I'm going to address them hopefully once for all. And I have a suspicion that these three students who asked me the questions, they did not have a chance to thoroughly work through the content. Okay, relatively new students working through the content, so might have speed up, and I don't remember seeing them in the live classes either. Okay, anyways, I'm a bit unsure about leading versus lagging power factor. Okay. And those of you who have attended, you know that after you've gone through the class, you should not be a bit unsure. You should be 100% solid on it and want to find out what is the sign positive, negative for the synchronous induction motor in some practice problems. So it's probably dealing with some practice problems and wanted to ask about this. I thought we have a leading power factor. If we have a leading power factor, we should have a positive angle. Again, a memorization type of an approach, right? Otherwise, it will be negative. Can you give me a hit on this? I think he's asking for a hint. Okay. Number two, I'm getting confused by the equation for power factor angle for leading versus lagging. In some places, it looks like the equation is negative cosine inverse power factor for lagging, but in other places, it is positive cosine inverse. power factor for lagging. Number 3, there is confusion for lagging and leading power factor. Sometimes, especially for currents, for lagging, you have used negative sign, and for others, especially for angle, you have used leading versus negative as negative. I think this was a question from you, Naz, early on, if I'm not mistaken, and I referred you to the live training. And I think you watched the live training and it probably addressed your question, correct? Can you please explain what to follow? Okay. All right. So let's take a look at this, guys. Let's start with first principles and hopefully for a final time. This is our triangle. It's called the power triangle, where the x component is the real component. Okay. This is the real power, P. This is the reactive power, Q. This is our apparent power. So if I write this as a complex power, S is equal to P plus JQ. Okay. If I want to figure out the magnitude, it becomes square root of P square plus Q square. All good? All right. Now the theta, the power factor angle, is tangent inverse of y over x, Q by P. Good. So the question is, basically all of these three questions are saying leading, lagging, how does it impact theta positive or negative? And then the third one is interesting. It takes a stab at the current. Okay. So there is some level of knowledge that you need to remember, baseline. And that baseline knowledge is simply the fact that when we consume, i.e., inductor consumes reactive power, it is considered positive. So when Q is positive, it means that the load is inductive in nature or has some inductive component to it. Okay, is that clear? If you have a perpendicular, big or small, in the positive x y-axis direction, it means that there is a Q, big or small. Since this is positive, this is an inductor. Okay. Inductors result in a lagging power factor because the current, resulting current, is going to lag behind the voltage. Okay. So when I have a lagging power factor, think of inductor, think of positive Q. When Q is positive, your angle theta is going to be pointing positive. It's going to be up. Okay. When we have leading power factor, think of capacitor. Capacitor is not a sink or a drain for reactive power. It is a source. It is a generator of reactive power. And if inductor, and this is a convention, consuming reactive power has a positive polarity, then a capacitor generating reactive power should have a negative polarity. That's why Q reactive for a capacitor is pointing downwards. When the perpendicular points downwards, what happens to the angle theta? Negative. Now, the interesting thing is, you guys can do this on your calculator. Do a cosine 45 and do a cosine minus 45. What is the answer? It's the same, right? What is the answer? 1, correct? I'm just going by my memory, and my memory is not great. It's 1, right, guys? Because sine 45, oh, no, sorry, half? What is it? Cosine 45, half, 0.707. So 1 divided by square root 2. And cosine minus 45 is also 1 divided by square root 2. Right? It's tangent 45, that is 1. Okay. Why am I bringing this up? I'm bringing this up because one of the students has correctly pointed out this. So by incorporating the sine of the angle, unfortunately, within the parentheses of power factor formula, which is cosine angle theta power factor, cosine theta power factor is not going to save you. Because if the angle is 45 or minus 45, because cosine is an even function, it is still going to be the same value. That's why you have to mentally, or somebody use the word manually. Somebody use the word manually, or I'm reading that here. Okay. So you have to mentally keep track of lagging versus leading. If it is a leading power factor situation, you're not going to keep the angle negative over here. You're going to take the angle cosine inverse, right? So cosine inverse, let's say power factor is 0.80, lagging. 0.80 lagging means that you are going to, when you're calculating the power factor angle, you're going to say that the theta power factor is plus positive. You're emphasizing, and you've seen me do that in several practice problems related to power factor, where I say it's going to be plus. Theta power factor is plus cosine inverse 0.80, correct? For lagging. Now, lagging sounds something like lazy, lazy sounds something like bad, and bad sounds something like negative. I think psychologically, this is the intuitive way of thinking that a lot of students have, and that's why they confuse this. Now, if I take this one step forward, theta power factor for a 0.80 leading load should be positive, right? Because leading means active, active means ahead, ahead means positive. Correct? Wrong. Leading power factor means that the Q is pointing downwards. So I have to manually, mentally inject a negative sign over here. Okay, guys? So please don't make this mistake. Understand from first principles and you're going to be set. So this answers the first two questions. Let me take a quick stab at the last one. And the last question is relating this back to current. Okay. Again, first principles, baby steps. Let's start with Ohm's law. V is equal to I R. Let's stick with IR. Okay. Now let us assume that we are dealing with, actually, you know what? Let's stick with IZ, and I'm going to create 3 scenarios out of that. Let's say that we are dealing with impedance, right? And phasor format. So I will be equal to V divided by Z. Let me bring your attention back to this portion of the question. It's saying that sometimes, especially for currents, for lagging, you have used negative sign, and for some other times, especially for angle, you have used leading as negative for currents. Okay. For currents, he's saying that you ended up, when the power factor angle was lagging, let me write this here. When the PF was theta was lagging, the current angle I, theta I, you ended up using negative. When theta power factor was leading, your theta I was positive. So now you can see that the student is taking one step forward. We are sort of talking about power factor angle, but we are not. Because he's tying this directly to theta I. Our discussion so far had been around power factor angle, that if the power factor angle is lagging, the angle is positive. If the power factor angle is leading, angle is negative. It's taking it one step forward. The unfortunate fact is that when it comes to the current angle, guys, we no longer have one player. When we were talking about the power factor, we were just looking at the complex power, the value of Q, positive or negative, right? When we are talking about the current, its phase angle can be impacted by voltage as well. And obviously, the impedance. Okay. All right. So let us keep things very simple. Okay. It's always a good idea to start with a basic framework and then build on top of it. For the sake of simplicity, let us assume that the voltage that we have has an angle of, so this is the magnitude of the voltage, and the angle is 0 degrees. Okay. This is my current and the current angle. It is equal to the magnitude of Z. I'm expressing this in the polar format. And Z has an angle theta Z. So what is this theta Z made up of? If you remember in the on-demand course and the live training, I explained to you guys that power factor can also be extracted, and the power factor angle can also be extracted from impedance triangle. Impedance triangle is similar to power triangle, but in the form of impedance. So this component, hypotenuse is Z, this is R, and this is X. So if we have an inductive load, Z is equal to R plus JXL plus pointing upwards. If it is a capacitive load, it becomes R minus JXC minus pointing downwards. Because the capacitive reactance is negative, and that's what leads to that negative sign in Q as well, QC. And the inductive reactance is positive. Anyways, the end result is that the impedance that is having an inductive reactance, so R plus XL type of a setup, will have an angle, power factor angle, that is going to be positive. So it is consistent because ZL is equal to R plus JXL, inductive, lagging, and theta power factor is positive. On the other side, ZC is equal to R plus JXC, correct? XC is negative, it basically is minus 1 divided by omega C, right? I should actually correct this. So it will have a negative component. This is capacitive in nature, leading, and because of this negative sign, you're going to have theta power factor negative. Okay. All right. So let's build on top of that. So if I'm working with ZL, inductive load, this is going to be a positive angle. And for sake of simplicity, we said that we're going to consider this as a reference, so 0 degrees. Can you guys see that the angle theta I is going to be V magnitude divided by ZL magnitude minus theta ZL. And this is actually V magnitude divided by ZL magnitude angle theta minus power factor. Because the theta of our impedance is the same as the theta power factor, right? Now, here's the thing, guys. Lagging power factor angle results in angle theta I, which is negative. Isn't it true? Theta I is negative for lagging. Again, if you take a memorization-based approach and don't have these concepts cleared out, at least during the preparation phase, you're gonna rely on these shortcuts. There's a rhyme and reason, and I've kept it simple. This guy could still end up being positive. Let's say this was 100 degrees for the sake of argument. This voltage phase angle was 100 degrees, and this angle was 50 degrees. Now it is no longer negative. It is 50 degrees. It is positive. So you might be wondering, Wasim, 1 second you were saying the theta power factor lagging is going to result in angle theta I negative. Now you contradicted yourself, right? How is it positive 50? Well, at the end of the day, the current angle is the difference between the voltage angle and the impedance angle based on Ohm's law. Okay. And if I have a leading power factor, yeah, just 1 second. Let me just finish this and then I'll take questions. If I have a leading power factor here, guys, ZC, this angle theta is going to be negative, right? Because it's capacitive in nature. You're going to see that this results in voltage divided by impedance, and this becomes 0 minus theta power factor, and this is V divided by ZC, and the angle becomes positive. So theta power factor leading results in angle theta I positive. Yes, but there's a caveat. I assumed 0 degrees over here, right? It could potentially be negative. If it's a huge negative number, minus 100 degrees, right? Hypothetically, and this is minus 50 degrees. So minus 100 minus 50 is still going to give me a minus 50. Okay. So hopefully this makes sense. The leading versus lagging business, the current angle as a function of voltage angle and the impedance angle. And please go through the on-demand content, step-by-step explanations, multiple practice problems that test you on this, details, homework assignments, and live training, and that should bring the point home. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, studyforfe.com.